Hi, my name is Kunal Mishra, and today we are going to discuss about the project which I have implemented using Neos True processor for making dot product and factorial program. This project was done under Professor Dr. Chang Chu, and this was my final project for the subject EE275. So moving towards the introduction. So what is soft core processor? Mainly, soft core processor are logic synthesis used in FPGAs. The typical characteristic of such processors are 250 MHz to or less than 200 MHz. They can be easily modified and tuned to specific requirement, more features, custom instructions, and etc. Multi-cores can be used at the cost of resources, but there is some limitation for that. The limitation is the speed of the fabric. As the speed of the fabric increases, the computation time also decreases. Now, moving towards what is Neos 2 processor. So Neos 2 processor is a processor which was built by Altera, and the processor have some instruction set cores which is reduced. It works on the RISC processor. It's also known as a RISC processor, and it is having a 32-bit embedded processor architecture. Mainly, Neos 2 have been used more towards the FPGA base or towards the DSP sides. It is having a high implementation on such fields, so suitable for the embedded computing application from DSP to system control. There are other FPGAs as well like Xilinx uh, and etc. But Neos 2 is the most basics and most standard feature, having a most standard uh, specification. Hence, they have been used in a wider range. Moving towards the architecture. So normally in this architecture, what we are doing is like there are different instruction set which is written in benchmark code, and this benchmark code are then turned out to into a Verilog code and after that they have been implemented. Normally the instruction set are in type of I, J, and R code of instruction sets are there. So we will be using those instructions into their opcodes, and then we'll be executing in our design and implementing them and simulating them. So you can see that what the main architecture the purpose of the main architecture is to describe an instruction set. It is used to implement in hardware and emulate in software and omit entirely. Its implementation is a set of design choice to achieve specific objectives, and it is a flexible and can be adapted for different target applications. Now normally the Neos 2 processor, what they have a 32-bit of data bus and 32-bit of address bus and register structures. With this specification, they even have a stack pointer. A stack pointer normally is of 32 bits, and they take 4 clock cycle to fetch and decode one instruction. So whenever you push an instruction inside a stack pointer, the address of that where the instruction is being loaded, it's after the complete loading of the instruction, it is decremented by 4. So the new stack pointer, so the new address of the data of the next instruction will be the -4 of the previous instruction. Similarly, when popping out the data of the of the topmost stack pointer is been used, and after that, once the data has been used, it is incremented by 4 and it is popped out. So on a basic or on a constant level of saying that the address of stack pointer is always 29, the frame pointer is 30, and the return address will be keeping as a 31. The block diagram of the pipelining over here, it shows how the exact pipelining takes place. Pipelining depends on various different stages, It can be 3 stage, 2 stage, 5 stage, etc. But normally we are implementing a 5 stage process over here. So mainly the pipelining will be having three basic type of execution. So first, the instruction will be fetched. After fetching of the instruction, it will be decoded. Once it is decoded, finding out what is the real they want to do, what the instruction really needs to do. After finding out that, then they will be executed. After execution, for the next instruction, if the instruction is having any dependency, it will be again going to the first level where it will be again fetched. So this counts the instruction cycle. So normally for a normal instructions like add, multiple, it takes one cycle, wherein it is stored or load, it will be taking 2 cycles. So while calculating the entire clock cycle for any instruction or for any implementation of uh, benchmark program, we'll be checking out the entire instruction home, which instructions are there, and accordingly we'll be finding out the number of cycles which will be used. If there is any loop, suppose for factorial, I need to find out a function for like 4 times. So I'll be using the loop for the 4 times. So the loop will be again multiplied with the number of instructions, and then we'll be getting uh, the clock cycles or the cycles which will be will be used for the execution of the instruction. Now moving towards the 5 stage pipelining, which will we have been implemented in this design. So the following diagram or the following page shows you the exact 5 stage of pipelining. So basically there are the main component of 5 stage pipelining is instruction fetch, instruction decode, execute, memory access, and write back. So initially from this memory, the instructions will be fetched. Once it is fetched, it is given to the registers. Over here in registers, it will be searched for its value. If there is any sign extended or some negative value, they will be going over this side, and then they will be proceeding towards the decoding part. At the decoding end, the instructions, the values will be fetched through the registers, and those value will be given for computation. Mainly in this executing cycle, the normal computation takes place, like ALU, normally arithmetic logic unit. So division, multiplication, all those operations will take place over here. After the operations is done over here, it will be the data will be sent out and towards the memory access. If there is any branching involved in it, so it will go towards the mux, and the program counter will be incremented, and again it will come back to the first to the fetching part. But it's if it needs to be loaded, so it will go to the memory. There the address will be again found out. After address, it will be right back to the mux, and from again it will go back, and it will get stored in the register files. So this cycle keeps on continuing till the execution of the last instructions, and this take normally this is the basic stage of pipelining, basic stage of pipelining where the execution will be taking place. So my dot product and factorial are on it's based on the this fundamental of you know fetching and executing and decoding the data, and I have been implemented this theory for my code. So once when I coded and simulated in VCS, so I generated some waveforms. So let's discuss those waveform in the next slide. So this is the simulation of the dot product. I've used Quartus 2 Altera to find out the compilation to compile my code. Once my code was compiled, uh, as there was no error and nothing, issues were found, I moved towards the simulation part where I simulated on other component like VCS. So after the simulation was done, the dot product, I got an answer 5T at 108 cycle. Sorry, it's at the 100th location of the memory, so it was stored over there. Okay, so the first operation is where the uh, ordering of uh, higher value higher value of bytes and lower value of bytes takes place. So the operand A, address operand A and address operand B are having two values. They have been OR together, and the result has been generated from by out, and then it is stored toward the another register, which is C. This was the first instruction which have been executed. From the second instruction, we get the opcode for load. Once the opcode is received, we will be putting into a load. We'll be loading those values into the register, and then again we'll be fetching the values from the register, and we'll execute, and then we'll decode it. We'll decode it and we'll execute after that. So over here you can see it. So the other operation was the ALU operation, which takes place in the fifth, which was the fifth instruction of the dot matrix, where the 4 is the value over here of the operand A, the 5 is the operand B value. The instruction was received from the opcode, and the result was stored in the was achieved at out register, and this value was stored into another register, so that the next vector or next A and B vector values can be generated, and it can be added to the previous value. After getting those values and getting generated, those values were then added after uh, few more iterations. After few more iteration, it was found out that the final answer of the dot product, which is over here, was achieved at according to this, it was achieved at 810 nanoseconds. This output was then stored at 100th location of the memory, and as you can see, when there is a read operation, the execution takes place, and as soon as there is a write operation, the storing takes place. So once the write signal is getting high, the value is been stored and the output is resetted, while the read operation will be continuing. So it totally depends upon the write operation, the signal by the write operation, and after the signal which is achieved by the write operation, the storing of the answers will be taking place. So this was about the for about the dot matrix, the dot matrix what we have done, the dot vector, sorry, the vector what we have done. Moving towards the factorial. So the code for the factorial you can see over here. There were some issues while doing the factorial code. As you can see, there was some problem with the jump instruction, because the jump instruction was not taking place properly, and so only for the first the iteration the value was generated in the output, and it was not even able to feedback to to the loop which was defined earlier, and because of that the entire function of factorial that couldn't take place properly. I guess there is was issues regarding with some jump code, and some issues with the pipelining part as well. That's why like the things were not looping back. Uh, this slide shows us the branching of the dot product, where the instruction, the address is been branched back towards the end again, and these things continue, and this can be improved by using more branch instructions, and by keeping it by data forwarding the instructions or the functions. So what analysis I made through my design is that by putting more clock cycles, I can avoid the stalling process where the data dependency is not there, so that everything can work properly. So what I've analyzed through this project, that the stalling can be avoided by providing more clock cycle, less hardware, less area, and lesser clock up period. And as well as the data forwarding can also be avoided by putting less clock cycle, comparatively more hardware required, more area, and large clock cycle, clock period. Moving towards the conclusion and the future scope, the above analysis gave a nice overview of dot product, where the dot product was calculated after a clock cycle of 96 cycle after 96 cycle. It can be more optimized by increasing the more number of pipelinings, where we can get an answer quite at a very minimum clock cycles. Whereas the factorial is need to be simulated and compiled more so that it can function properly and execute all the possible values given to it. Hence, the project is concluded with satisfactory results. For more details and in-depth analysis, you need to go through the report of this project. And thanking you for the patience for hearing me. And have a good day. Thanks.